Hello everyone, welcome to lecture 3 of week 3, which is continuation of the module Synchronous Generators in this course Power Network Analysis. In this discussion, we will continue with capability curves, and in the previous lecture, we had briefly touched upon one aspect of capability curves, which was built on the discussion that we had regarding real and reactive power expressions for synchronous generators, to be specific. So if we recollect, uh, like any other electrical equipment, synchronous generator also has certain ratings, safe operating points, which are constrained by typically three limits. The first one is maximum armature current limit or stator current limit, which in a way indicates what is the maximum current that can flow in the three-phase stator windings. If the current exceeds this maximum armature current limit, the stator windings may get damaged, the associated insulation may also get damaged. Similarly, there also comes a limitation in terms of maximum current which the rotor winding can carry in the synchronous generator. Rotor winding is also known as field winding, and hence the field current goes analogous to the rotor current, which is DC current. And there is also a maximum limit to it. If rotor windings carry current beyond this maximum field current limit, then the rotor windings can get damaged, the associated insulations may get damaged. And indirectly, since the induced EMF, if we recollect the lecture discussion on induced EMF, where we also talked about armature reaction, generator being loaded and unloaded, in that discussion, we also saw that the field current or rotor current in a way influences the EMF which is induced in the three-phase stator windings, which in a way can also result or can also be replicated as equivalent maximum limit on this induced EMF that can be generated without compromising the safety of rotor winding or the rotor insulation. So in a way, the field current limit maximum can be linked with the maximum of the induced EMF or associated voltage. And the third constraint which comes from synchronous generator perspective is the maximum power that can be extracted from this synchronous generator without compromising the stability limit, and that's where the maximum steady state limit comes in, which is going to be a discussion of length in the last module on stability analysis. In this discussion, we will only understand where does this limit come from and what is the associated numeric value. More details of the stability limit will come in the last module of stability analysis. The synchronous generator or machine that we have considered, it was also discussed or told in the previous discussion. To just make it more clear, the synchronous generator or machine that we have, it's a cylindrical pole machine with negligible winding armature winding resistance. So that is what the machine we are considering. The discussion that we have can also be applied to salient pole machines or similar lines. We are not discussing salient pole machine capability curves for the sake of simplicity. And this synchronous generator or machine, which is cylindrical pole, often would operate at a rated terminal voltage, which is Vt, with a fixed synchronous reactance Xs, and this synchronous reactance is being considered to be fixed. The non-idealities or non-linearities involved in between the rotor air gap or the stator, the air gap in between rotor and stator, that is being neglected for time being. So with this as our premise, we had looked at this locus with respect to armature current limit, which is essentially coming from the first limit that we had discussed in the previous discussion. This limit pertains to a fixed terminal voltage. There is no need of synchronous reactance while defining this locus, because the maximum armature current limit in a way is indicating what is the maximum amount of armature current per phase which can flow in the stator winding, which can be replicated or transferred as that if Ia max is the corresponding maximum armature current limit and Vt is the specified terminal voltage at which the machine is supposed to operate, then the corresponding apparent power that can maximum be handled by the synchronous generator will at best be Vt into Ia max. And we also know that apparent power square is nothing but sum of square of real power and reactive power. So P is real power and Q is reactive power. So in a way, if I have to understand this locus is essentially telling me that P square plus Q square can at best be equal to Vt into Ia max square. The expression, the equality that I have written, it can have a less than equal to form, but definitely not more than equal to form. If the current goes beyond Ia max, the stator winding may get damaged. So if in a way, if I have to understand or plot this curve on a PQ plane, which is the complex plane with P as the x-axis and Q on the y-axis, this equation is very similar to the equation of a square on a xy plane, which indicates that if x square plus y square is equal to r square, then on a xy plane, this equation represents a circle with center as with origin as the center and r being the radius. So if we apply the same notion, we have the armature current limit as all points inside this circle whose center is the origin and the radius is Vt into Ia max. We also understood what is the blue, green, purple and orange regions. All points on the right hand side of Q axis pertain to generating mode, whereas all points on the left hand side of Q axis refer to motoring mode. Because on the right hand side P is positive, P positive means the machine is delivering real power, so it is behaving as a generator. For the left hand side of Q, P is negative, so machine is behaving as a motor, so it is consuming real power. Similar notion can also be applied for points which are above and lower the p-axis. Points above the p-axis, the reactive power is being delivered or generated by the machine. So in that sense, the blue and the orange colors, they refer to overexcited mode, whereas points below the p-axis where Q is negative means the machine is absorbing reactive power, we would call them to be underexcited mode. We'll talk more about overexcitation and underexcitation in the next lecture. And for a specific point or a specific angle, theta is equal to 0 degrees, where theta is the load impedance angle, the corresponding power factor would be equal to 1. And the notion of why theta is marked like this over here is because if S is the radius of this circle, then S cos theta would be the real power, which is this measure, and S sin theta will be reactive power, which is on the y-axis, and that's how the angle theta can be marked. So theta equal to 0, meaning theta can be 0 both for generating mode, which is this yellow color line. It can also be 0 for the motoring mode. And that's how the yellow color line represents unity power factor operation where no reactive power exchange is happening. Building on this, now let's talk about how do the locus for maximum field current limit looks like. As already mentioned, maximum field current limit, if the current is beyond this limit in the rotor winding, it may damage the rotor winding as well as the corresponding insulation. And since the field current is responsible for creation or induction of this induced EMF in the rotor winding, so IF max value can be correlated as the maximum excitation voltage, not the terminal voltage, for a given synchronous generator. The reason why any operation beyond maximum induced EMF is prohibited comes from the open circuit characteristics of the synchronous generator, beyond which if on the open circuit characteristic any point is operated beyond the saturation point, it may damage the stator and rotor cores, it may affect their magnetic properties. And as already discussed, every such field current limit, armature current limit or steady state limit, the corresponding locuses would pertain to a fixed terminal voltage and fixed synchronous reactance for a negligible armature winding resistance cylindrical pole synchronous generator. So if we have to understand the locus or corresponding mathematical expression which comes from the maximum field current limit, it is essential that this locus or equation that we are trying to find, it should be in terms of known quantities, not the unknowns. Given that the machine is operating at fixed terminal voltage, fixed synchronous reactance, and the maximum induced EMF value is known from the corresponding maximum field current, it is imperative that the locus or equation which we should derive to understand the field current limit locus should be in terms of these three encircled items. So if we start from the basics, we already understand or know that for a cylindrical pole generator, synchronous generator with negligible armature winding resistance, this is the expression of per phase armature current. Again, please note that subscript A here doesn't mean phase A. Subscript A here is indicating armature winding. So if this is the current expression for cylindrical pole generator with negligible armature resistance, we can also expand this current into corresponding real and imaginary parts. So if we do that and focus on the term sitting over here, we will most likely have, not most likely, we will definitely have one real part as well as an imaginary part. The real part would be of the form EF cos delta minus Vt. Pardon me for the mistake in defining real and imaginary part. Let's look at how this expansion looks like. So if we expand EF at an angle delta as EF cos delta minus Vt is sitting over here, then we'll also have J, which is the complex root or imaginary number, root of -1. It will be EF sin delta divided by J of xs, which if expanded would look like EF sin delta by xs minus J EF cos delta minus Vt by xs. So the first term here is the real component of armature winding current, and the second term here is the imaginary component. Now if we take or try to find the magnitude of this armature current, what we can do is we can probably evaluate. Let's say if we do it here, let's say we take the square of mod of Ia. So it should look like Ia mod square should be equal to square of this real term, square of this imaginary term, and then addition of both of them. So if we do that, it should look like EF square by xs square sin square delta plus EF square cos square delta by xs square plus Vt square by xs square minus 2EF Vt cos delta by xs square, wherein if we see the first two terms, they can be added together and we would simply have EF square by xs square followed by Vt square plus xs square and then this cosine term. So from there, if we, let's say, have this sort of an expression where Ia square is defined in terms of induced EMF, terminal voltage, cosine of torque angle and synchronous reactance, we can then further elaborate it more. We also know from armature current limit locus that P square plus Q square for a cylindrical pole or any generator, it is equal to Vt square into Ia square. Why? Because P is nothing but Vt into Ia, which is the apparent power cos theta. Theta is the power factor angle and Q is Vt Ia sin theta. Depending on the power factor angle, Q can be positive or negative. So from here we get this expression. So essentially we can have P square plus Q square is equal to Vt square plus Ia square. And now if we substitute Ia square into this term, it looks little complicated, but when you plug in those numbers appropriately, we will have this as our equation. Now what we see here, we see that for defining the locus, P square plus Q square are the obvious terms because we are trying to plot this locus or limit on the PQ plane. The third term is also okay because Vt is fixed, synchronous reactance is also known. The last or the fourth term on the right hand side or the left hand side, pardon me, is a troublesome term because with change in the excitation current, it is not just the induced EMF that will change. The corresponding torque angle can also change. So what we need to get rid of or to have a equation which is defining the maximum field current limit only in terms of known quantities, we have to figure out a way how this term, which is carrying a variable quantity, specifically cosine of delta, can be avoided or can be substituted. So let's try to see how it can be done. Before we do that, let us try to recollect the real and reactive power per phase expressions for a cylindrical pole machine with negligible armature resistance. If we recollect or revisit our previous lecture discussion, we remember that real power for cylindrical pole machine with negligible armature resistance is nothing but EF Vt sine delta by Xs, and Q is nothing but Vt into EF cos delta minus Vt entire term divided by Xs. Now, if we try to look at the terms which are residing in this, we can probably figure out that this particular term, which is EF Vt cos delta, it is also being present partially in the expression of Q. So, can we make use of this EF cos delta term sitting in the reactive power expression and try to substitute this over here? If we do that, then this is what equation which is what I was trying to refer to. EF Vt cos delta by Xs can be simply written as Q plus Vt square by Xs. And now if we substitute this term in the term or expression over here, it would simply be all the terms that you would see after substitution, they would all be in terms of either P or Q or only in terms of the known quantities. And a little simplification would reveal that the locus for maximum field current limit, wherein EF max is the maximum induced EMF because of maximum field current limitation from the operation perspective, can be again defined in form of a equation as a circle on the PQ plane, whose center is 0 with minus Vt square by Xs as coordinate, and the radius of the circle is EF max Vt by Xs. So, if we plot this circle on the PQ plane again, this is the green color locus, that how it would look like. All points inside this locus are the safe operating points for the synchronous machine. Any point beyond this circle would indicate that we are trying to operate the machine at an induced EMF which is more than EF max for fixed terminal voltage and synchronous reactance, which may sort of compromise the safety of the rotor winding and the insulation. So, all points inside this circle are safe operating points. All points outside this circle are prohibited operating points from the perspective of maximum field current limit. And if we also look at the expressions for P and Q that we saw for a cylindrical pole machine, let's try to look at that. So, we remember P is EF Vt sine delta by Xs and Q is Vt EF cos delta minus Vt by Xs. Using these expressions, is there a way to mark the angle delta on this PQ complex plane that we have? Now, if you look at the first term of real power, it is EF Vt Xs, which is also similar to the radius which we have over here. So, if we have to find how delta should be marked, then suppose we know that delta, the corresponding sine component, if it is multiplied with the radius of the circle, should be nothing but the real power. So, the way we mark the load impedance angle in armature current limit discussion, if we do a similar analogy here, it would be pretty obvious that the angle delta is nothing but the angle of this radius with respect to the reactive power axis, because if we take the sine of this delta marked over here, it would essentially be a component which is shown as the dotted line, which would indicate the corresponding real power which is being generated or absorbed by the corresponding synchronous machine. So, that is how we can know how the delta angle can be marked. This also goes well with the expression of reactive power, because if sine delta is the component over here, then the corresponding perpendicular line would be the cos delta, which is nothing but Vt into Ef cos delta by Xs, and in order to find the total reactive power, the Ef cos delta by Xs term has to be subtracted by Vt square by Xs, which is inherently sitting over here. So if we all combine or merge these ideas, then this is how the delta angle looks like, which is the torque angle or the power angle. And now if we look at the third constraint which comes from the steady state limit, it was also talked about in the previous discussion that any operation of synchronous machine for angle more than 90 degrees, torque angle being more than 90 degrees, is a prohibited operation because the generator might lose its synchronism. It's a stability concern which we will discuss at length in the last module. Just to sort of compromise or just to collate how steady state limit locus would look like, it is defined by the fact that for a cylindrical pole synchronous machine with negligible armature resistance, this is the expression for real power. Any angle of delta more than 90 is prohibited. So in a way, this limit here is indicative of the steady state limit. If this is the limit of steady state limit, Pmax equal to Ef Vt Xs for fixed terminal voltage and fixed synchronous reactance and for fixed field winding current, then is there a way to mark this locus or limit on the PQ plane? Yes, the locus can be obtained from the locus or from the field current limit itself. So let's see how do we do that. And that was the reason why we had a discussion on how the torque angle or load angle can be marked. That was the necessity. So now if the load angle is the angle of radius with respect to reactive power axis, delta is equal to 90 degrees would essentially mean in the generating mode that the corresponding radius, instead of being in this notion, for delta is equal to 90 degrees, it would mean that this radius has rotated and the angle which is now being formed is equal to 90 degrees with respect to q axis, and probably this is the line which is the maximum steady state real power which can be delivered by the machine in generating mode. A similar line can also exist for delta is equal to minus 90 degrees, where delta is negative for motoring mode. This is the corresponding limit which can be absorbed by the synchronous generator, cylindrical synchronous generator in the motoring mode. So if we know or understand that having defined the angle delta and delta is equal to plus 90 for generating mode, delta is equal to minus 90 for motoring mode, which defines the steady state limit, then essentially this blue line is the locus line, which is the steady state limit. Now, is there a way to have a numeric equation which defines this blue color steady state limit? So essentially, all points which are above this blue line indicate the safe operating points. All points below the blue line are prohibited points because torque angle would be more than 90 numerically, which is not allowed. So all points above this limit or line are blue line are the safe points. Now, is there a way to find this equation which identifies this blue line similar to the locus line for the field current limit or the armature current limit? If you closely look, this blue line is a line which is parallel to the p axis and it is crossing the q axis at a point 0 with minus Vt square by Xs. So if there is a line which is parallel to the p axis or x axis, its equation is by default in terms of q or y axis. So if we have to write the numeric equation for this blue line, it is nothing but q is equal to minus Vt square by Xs. This is a generic line which can extend beyond these blue line. The blue line is getting limited by the fact that a synchronous generator has to abide by all limits at a given particular point. So this blue line is fraction of this dotted line limited by the steady state limit, because remember, all points inside the steady state limits are also safe points from field current perspective. So in a way, this entire section of line is coming from superimposition of field current limit as well as steady state limit, which is for the angle delta is equal to 90 degrees. And q is equal to minus Vt square by Xs is the numeric mathematical form for defining this blue line. So now if we sort of superimpose or combine all of this, locus of field current limit is a circle with center at 0 minus Vt square by Xs and radius as Ef max Vt by Xs. Steady state limit is a line parallel to p-axis with equation defined as q is equal to minus Vt square by xs, and it is also limited on both ends by the field current limit locus. All operating points below the steady state limit locus are inoperable as the machine might lose synchronism. So if we draw or plot the feasible operating points or safe operating points for this synchronous generator which is cylindrical, then on similar lines the way we had armature current limit locus, we have our generator limit locus for both overexcited and underexcited operation. We also have our safe operating limit for motor for both overexcited and underexcited operation. The yellow line still pertaining to unity power factor point. And now just to sort of pick up your brains, if we have to find these specific points on the PQ plane, that's where the equations of blue line and the green color line would come into handy. If we were to find the point which I have marked over here, then this point would typically be EF Vt, let's say EF max to be specific, EF max Vt by xs with minus Vt square by xs at the corresponding Q point, and similarly this point over here is nothing but the intersection of blue line and green line. So here we would have minus EF max Vt by xs comma minus Vt square by xs as the corresponding P and Q axes. We can also verify these points by revisiting the equations for field current limit locus and steady state limit locus. Now remember, when we are drawing all these points, we still have one more limit which we discussed in the last lecture and any machine at any given point of time has to abide by all operating points. So it's time to superimpose the armature current limit locus on these two locuses. So if we do that without marking the underexcitation or overexcitation points, then the armature current limit locus equation was P square plus Q square is equal to Vt into Ia max square. The green color equation was P square plus Q plus Vt square by xs whole square is equal to EF max Vt by xs square, and the blue color line equation is Q is equal to minus Vt square by xs. If we have to identify the common operating points, the common operating points should be all points which are overall safe from all limits perspective. So for the armature current limit, if you recollect, all points inside the black circle are safe points. For the green color locus, which is the field current limit locus, all points inside the green circle are common or feasible points. And from steady state limit perspective, all points above the blue line are safe points. So if we now try to find a set of points which are common to these three sets, the black circle set, green circle set, and points above the blue line, the only safe point which would appear are the areas which I have been marking over here. On the P side, positive P side, the armature current limit locus is limiting the safe operating points. On the top, we have the field current limit locus limiting the points. On the below, we have steady state limit, and similarly on the LHS, we have the safe operating points from armature current limit locus. So if we now mark or figure out the common points, this is the locus which looks like from the operating limits restrictions. And now if we mark our generating or motoring modes for underexcitation, overexcitation, those points, they look like this. So this in a way is the overall capability curve, the one which is shown over here for a cylindrical pole synchronous generator operating at synchronous mode with negligible armature winding resistance. In the next lecture, we will take up our discussion on finding out how the real power and reactive power of a generator, synchronous generator, can be controlled physically through certain action points. Thank you.